Thanks for joining me, people, for another Juddy Productions video. Today's video we're looking at motion graphs, in particular velocity time graphs, and this is example number 2. If you've not watched video example number 1, maybe watch that first as well. So let's examine this graph. Question number 1. What was the acceleration of the object over the first 10 seconds? So first of all, looking at the first 10 seconds of motion, which is coloured in blue, you can see how velocity increases at a regular rate. This is a constant period of acceleration. We know that acceleration is equal to the gradient of this graph, and the gradient is of course rise over run. So the rise in this blue section, the first 10 seconds, on the vertical scale, our line starts at a velocity of 0 and goes all the way up to a velocity of 20. So there is a rise of 20 meters per second. The run is on the horizontal axis, starts at a time of 0 and goes across to a time of 10. So the run is 10 seconds. Let's sub those values in. So acceleration is 20 meters per second divided by 10 seconds. 20 divided by 10 gives us the value of 2, and meters per second divided by seconds gives us a unit of measurement of meters per second squared. And because this line is a positive gradient and our positive velocity has a labeling towards the north, this represents 2 meters per second in a northerly direction. A quick point in terms of acceleration units. Acceleration is equal to the rate of change of velocity. So it is meters per second. That's one way of representing it. That can be further summarized to meters per second squared, or using this alternative notation, ms to the negative 2. The negative effectively represents the per in our meters per second squared. All three of these options are correct and can be used interchangeably. Question number 2, what was the acceleration of the object over the final 8 seconds? We colour that in blue. Again, acceleration equals gradient, and gradient equals rise over run. So the rise, how far it's changed in the vertical scale. Over the last 8 seconds, we start at a velocity of 20 meters per second in the north, and we go all the way down the vertical direction to a velocity of minus 20 meters per second north. So this rise could really be described as a fall of 40 meters per second, but mathematically it's a rise of negative 40 meters per second. The run is on the horizontal axis. At the start of this section, we're at a time of 14, and we run across to a time of 22. That represents a run of 8 seconds. So acceleration is our rise over the run. It's negative 40 meters per second divided by 8 seconds, and that gives me a value of negative 5 meters per second squared in a northerly direction. All our reference directions are northerly, and this is a negative gradient at a downhill slope. So it's negative 5 meters per second squared north, which alternatively could be written as 5 meters per second squared in a southerly direction, because the negative of north is south. Once again, our units of acceleration can be written as meters per second, meters per second squared, or meters per second to the negative 2. Question number 3, what was the distance travelled by the object over the entire journey? Now recall that distance equals the area under the graph, or another way of expressing this is the area between the line of the graph and the x-axis. So that's an area of a trapezium and an area of a triangle. The trapezium is shown in blue and the triangle is shown in yellow. First of all, let's look at the area of the trapezium. The equation for the area of a trapezium is half in brackets a plus b close brackets times h. So in a trapezium there's two parallel lines, one up the top and there's a parallel line on the bottom. A, in this case I've chosen the shorter of the two parallel lines, and it travels from a time of 10 seconds across to a time of 14. So the difference between 14 and 10 is 4. So A has got a value of 4. B is the other parallel line, the larger one, and on the x-axis it runs from 0 all the way across to 18. So B has a value of 18. H, the height in the vertical direction, is from 0 up to 20, so H has a value of 20. We substitute in those values, and 4 plus 18 gives me 22, times a half of 22 is 11, times 20 gives me 220 meters. Okay, so that trapezium has an area of 220 meters. Let's work out the area of our yellow triangle. And of course the equation is a half base times height. So there's a base of this triangle along the horizontal axis from 18 across to 22. The difference between 22 and 18 is 4, so it's 4 units across. And the height of it is 20. So we start at a value of 0, and it goes all the way down to a value of 20. Working out the area, we're not worried about positives and negatives, so it's got a base of 4 and a height of 20. 4 times 20 would give me 80, and half of that would give me 40. So that represents an area of 40. Adding them together, we end up with the total distance travelled by the object shown in this velocity time graph of 260 meters. 220 meters above the x-axis, that's in the north direction, and a further 40 meters below the x-axis, that's in the south direction. But distance isn't worried about direction, it's simply the sum of the 220 and the 40. Final answer of 260 meters. Question 4, what's the object's displacement at the journey's end? We know in the blue trapezium we have a displacement of 220 meters to the north, and in the yellow triangle we have a displacement of 40 meters to the south. Displacement is adding those two together, so 220 to the north plus 40 meters to the south. When you're adding a south to the north, adding 40 meters to the south is the same as taking 40 meters north because we're traveling backwards. So in fact, that gives me a total displacement of 180 meters to the north. Question number 5, was the object ever stationary, and if so, when? No, the object was never stationary. We can see that for the first 10 seconds, the object experienced constant acceleration, so it's moving. The next 4 seconds, the object experiences a constant velocity of 20 meters per second, so it's moving. And then in the final 8 seconds, the object accelerates in a southerly direction, but it never remains stationary. Question 6, during what time interval or intervals, if any, was the object traveling north? We just stated the object was traveling north while the line was above the x-axis, and that represents from time 0 to 18 seconds. Question 7, during what time interval or intervals, if any, was the object traveling south? And we also just stated the object was traveling south while the line was below the x-axis. So that represents a time from 18 to 22 seconds.
You've been watching a Juddy Productions video. If you've enjoyed and indeed learned something from this video, then please remember to like, share, comment, and subscribe. And as always, thanks for watching.